Okay, this is Chapter 4, Dynamics, and I'm going to introduce Newton's 3 laws of motion. So up until this point, I've talked about motion, position, velocity, and acceleration, but I haven't talked about what causes the acceleration, or the change in velocity over time. So I'm going to do that by first talking about forces, and I'm going to talk about the 3 laws of motion that are related to that. I'm going to talk about 2 very important quantities, mass and weight, and make the very clear distinction that mass and weight are very different things. We're going to learn about drawing some free body diagrams, very important skill to have, and we're going to talk about friction and motion on an incline as well, so lots to do. So a force is a push or a pull. If an object is just sitting there on the table, it's not moving. To get it moving, we need to apply a force. This force is going to cause it to change its velocity. That's also known as acceleration. So here's an example of a force that is a push, and an example of a force that is a pull. And we can measure the magnitude of force using something like a spring scale, where if we know how stretchy a spring is and how far it's pulled, then we know how much force was applied to move this case of olive oil. A force has a unit of a Newton, so that's the symbol for it, and it's spelled just like Isaac Newton, the fellow who came up with the Newton's 3 laws. So jumping right into Newton's first law of motion, it's often called the law of inertia, and what it says is every object is going to continue in a state of rest or in uniform velocity in a straight line so long as no net force acts on it. So what that's saying is if you have an object that's sitting on a table, that object is just going to keep on sitting on that table until you apply a force to it, and then it's going to move. It will no longer be in the state of rest. We could also have a ball, and this ball is rolling with some velocity. If there is no net force acting on this ball, then it's going to continue at a uniform velocity in a straight line. Now in the real world we have stuff like friction. Friction is actually a force, and eventually someday this ball will come to a rest, but if friction did not exist, then that ball would continue in the straight line forever. One word I want to talk about is net force. If you consider somebody giving a box a push with a force over here, and someone applying a force over here, call this force B and this one force A, then the net force, or the sum of forces, you can also write that as force net, is going to be equal to force A plus force B. That's going to be the net force on this object. And since they're in opposite directions, it could be that they cancel each other out. Now, one thing about Newton's first law of motion is it is only valid in inertial reference frames, and essentially what that means is rotating and accelerating frames do not follow Newton's first law of motion. And if you think about it, if you're looking at somebody on a playground and you're standing on the merry-go-round and you're going around and round and round this merry-go-round, your velocity is always changing. At this point your velocity is in that direction, at this point your velocity is in that direction, at this point your velocity is in that direction, and at this point your velocity is in that direction. So you are accelerating, your velocity vector is changing. And if you're trying to look at somebody, you're seeing them essentially come closer and go further away, come closer and go further away, come closer and go further away, but there are no forces acting on that person. So that motion is not caused by a force, it's caused because you're in a reference frame where Newton's first law is not valid. Another concept that I need to introduce is mass. The mass of something is a measure of how much inertia it has. And inertia is essentially the resistance to motion. If you think about two objects, let's say a car and a 18-wheeler, the 18-wheeler has a lot more mass, it also has a lot more inertia, and if you wanted to try to push a car to the side of the road versus push an 18-wheeler to the side of the road, the 18-wheeler is going to resist the motion a lot more than your car is. In the SI system, mass is measured in kilograms. I introduced that on the first day. And one very, very, very important concept is mass is not weight. Mass is a property of an object, a physical property of the object. Weight, on the other hand, is actually a force. Because it's a force, it's going to have a unit of newtons, and this force is exerted on that object by gravity. They're related. I'll get into that in a little bit, but mass and weight are not the same thing. So if you were to, for example, go to the moon, where the gravitational acceleration is much lower than on Earth, it's actually 1.6, your mass would be the same as it was on Earth, however your weight would be much, much, much less. Newton's second law of motion is actually an extension of his first law. The first law said that an object's going to remain in motion or stay at rest until an outside force acts on it. And his second law creates a relationship between the force, the net force that we were talking about on the first law, and it relates it to how much an object accelerates. It turns out that the mass is important when it comes to this. So Newton's second law is very often written as the sum of forces is equal to the mass times the acceleration. We could also say that the net force is equal to the mass times the acceleration. I'll draw my little vector symbols on here because they're important. So what that says is if you apply a force to something, it's going to accelerate, and how fast it accelerates depends on how massive it is. If we wanted to think about our acceleration being equal to the net force divided by the mass, all I've done is I've divided both sides by mass. Then if I can only apply a force of, let's just say 1, then the acceleration would be equal to 1 over the mass. And what that says is, the more massive an object is, if you consider a mass of 1, the acceleration would be 1 meter per second squared. And if you now consider something that's a lot more massive, maybe it has a mass of 10, then for that 1 Newton worth of force, my acceleration will only be 1/10 of a meter per second squared. So if you've ever driven a load full of people in your car, it feels like it's harder to accelerate. It's because of Newton's second law. You have more mass in your car, and your car has a limited amount of force that is available to it. Now, one thing that is nice about force being a vector, it means that Newton's second law must be true along each coordinate axis. So I could say the sum of forces in the x direction must be equal to the mass times the acceleration in the x direction, and similarly the sum of forces in the y direction must be equal to an object's mass times the acceleration in the y direction. And that's nice because I can take complicated problems where if I have an xy system and I have a force that is going off at some angle, then I can break that into its components and I can solve Newton's second law of motion along each one of those lines of each one of those coordinate axes. Let me just reiterate again that the unit of force is the Newton, and you can kind of see right here that a Newton is actually just the name of it. A Newton is defined to be a kilogram meter per second squared. The unit for mass is kilogram. The unit of acceleration is meter per second squared. So you can kind of see how Newton's law works out with the unit of Newton. Let me also just say really quickly, looking at table 4.1, that in the British system that we're used to, the unit of force is pound. This is why people often get confused and say that mass and weight are the same thing, because we're used to the British system where the unit of mass is slug. We tend to think, of how much our weight is, how much force we apply to the ground as how massive we are, but that is not true. The weight is not equal to the mass, and you can clearly see that in the units of the SI system. Newton's third law of motion, you may have heard the phrase for every action if an equal and opposite reaction. That very well may have came from Newton's third law of motion. Now what this says is any time that a force is exerted on an object, that force must be caused by another object. So a very wise physicist kind of explained this to me by saying you can't be touched, or you can't touch without being touched. If I put my hand on the desk, I feel the desk also feels me. So anytime there's a force exerted on my hand, it must be caused by another object. It cannot come from within my hand. So more concisely, Newton's third law says whenever an object exerts a force on a second object, the second object exerts an equal and opposite force, or an equal force in the opposite direction of the first. So we have, the two objects here, and the way that the book kind of describes it pictorially here is if you take your hand here and you exert a force onto the desk is going to exert an equal force, equal in magnitude, but opposite in direction back on your hand. This is fairly simple to state, but identifying these pairs of forces, these action-reaction forces, are sometimes difficult. This would be the action force, and this would be the reaction force. So, just to think about this a little bit more, we need to, again, just say in italics here that forces are exerted on different objects, and you want to make sure that you don't use them as if they're acting on the same object. What you can think of here is if you consider an ice skater that is on some frictionless ice, and she pushes on the wall with a force, the wall is going to push back on her. So we have our two objects, we have our forces of equal magnitude in opposite directions. You can kind of look at that and you might say, I have one force to the left and one force to the right, so the net force here, the sum of the forces, is going to be equal to 0, but that is not true because these forces act on different objects. This force right here acts on the skater, and this force here acts on the wall. It's the force of the wall on the skater that causes the skater to accelerate in that direction. So we have to be careful about which object we're looking at. Newton's third law also explains rocket propulsion, where if you have a rocket here, and this rocket is spewing out hot exhaust, hot fuel, there was a force needed to do that, and therefore there must be an equal and opposite force exerted on the rocket, and more importantly, this is the reaction force right here that is acting on the rocket. And why that's important is rockets actually don't need anything to push against. All they need to do is to be able to push this fuel out of the tail. Rockets obviously work in space. In space it is a perfect vacuum, so there is nothing to push against in space. So it's Newton's third law that allows rocket propulsion to work. So one helpful notation to look at when we consider Newton's third law of motion is to write it such that we're using subscripts on our forces, where the first subscript is going to be the object it is the force is being exerted on, and the second would be the source. So if you consider somebody walking right here, the force of on the ground due to the person, ground being the object, person being the source, is going to be right here in this direction, and the force of the person, or the force on the person due to the ground, the force on the person due to the ground can be written like that. Now Newton's second law says that these are equal in magnitude but opposite in direction. So I have the negative sign. Now, and the interesting thing about this person walking example is we know that we're applying a force on the ground that is actually in the backwards direction. What propels us forward is the force of the force on the person due to the ground, and in this case it's in the opposite direction. It's in the direction from the left side of the screen to the right side of the screen. This is what propels us forward, and it's because we exerted a force in the backward direction on the ground. So the ground is essentially pushing us forward. Now you don't need to necessarily do this indefinitely, and you could actually even write it, in long script. You could say the force of the force on the ground by the person, rather than writing the FGP. But it's very important that you know, and can convince me that you know, which forces you're talking about, because forces always come in pairs, and if we're looking at the wrong object, then the directions are going to be wrong. So make sure that this does not confuse you which force you're looking at.